So today is July 3rd, the third day of July. Tomorrow is a holiday, July 4th. And I'm going to continue with the material here. What I want to do, we are writing here, okay? And we're going to look at not just relativity, but then we're going to come back to chapter 17 as well. We didn't have time to cover chapter 17, everything in chapter 17, but we're going to cover now. It's going to do Doppler effect. Doppler effect. And then we're going to get into the relativistic Doppler effect. I want to cover the regular Doppler effect before we cover the more difficult one, which is the relativistic Doppler effect. And that's going to be version 7 right in here. What else you have to know? Okay, we will go back. Let's make sure it's chapter 17, right? So we have everything correct here. Wiley plus Wiley course resources. And let's launch it. Speed of, so yeah, the Doppler effect. So we didn't cover everything here, but we did cover speed of the sound, traveling sound waves, interference. We didn't cover intensity and sound level. I'm not gonna do that. We covered this one, beats, and we're left with those two here. Doppler effect and supersonic speeds, shock waves. We go back to chapter 17 and cover Doppler effect, the regular Doppler effect, before we cover the relativistic Doppler effect. Okay, and what is okay? It was okay, Sartak. It was a minor update here, Sartak. Going back right in here and today, okay? So I'm just adding the Doppler effect on chapter 17 here to today's activity. Okay, we need to learn about the regular Doppler effect before we start talking about the relativistic Doppler effect. Okay, that's the only thing that I have updated here in the schedule of classes. Okay, so what is the Doppler effect? Doppler effect is a shift in the frequency of a source that you observe. The regular Doppler effect is a shift in the frequency of a source that you observe whenever there is relative motion between the observer and the source of the waves. Okay? So the situation goes like that. If the source of the wave is at rest with respect to an observer, you measure a given frequency or period, right? A given frequency or period. One example, I'm going to give you an example of real life example, right? Real life example, an ambulance at rest with respect to you and its siren on. The siren has a specific frequency. You hear a specific frequency from the siren, specific frequency, I'm gonna call that F from the siren, when it is at rest with respect to you. Okay? Put the ambulance, when the ambulance moves towards or away from you, you hear a different frequency that I'm going to call it F prime. This is an actual phenomenon that happens. That's why they have that Doppler radar that we hear about, right? Let's take a look out there. Doppler radar that we hear about in the TV. Doppler radar. So they use the Doppler effect to find out how fast a cloud is moving towards you. Okay, that's one of the applications of the Doppler effect. And let's go ahead and try to visualize this Doppler effect. Let us visualize this Doppler effect. Okay. Again, we are going back to chapter 17, okay, to cover the regular Doppler effect before we go back to relativity and start talking about the relativistic Doppler effect. Now we start with a very simple type of wave, C wave. An ocean wave, right? Simple type of wave, an ocean wave. Think about an ocean wave in the open sea. In the open sea, not the waves that you see at the coast, not the waves we see at the coast, okay? There's an important difference between the ocean wave in the open sea and the wave in the sea coast. Okay, there is an important difference between these two waves. Okay, the one that we're most familiar with is the wave in the sea, in the coast, at the coast, at the beach, at the coast or the beach. A wave at the beach, a wave when it approaches, when a wave approaches the beach, it breaks down and produces a white foam. Okay, it's going to be white if the beach is not polluted, right? But if the beach is polluted, the foam is not going to be white. It's going to be dark. I have seen those foams, those waves in a polluted beach. Okay, there's a reason. There is a reason. Why the wave breaks up at the beach. There's a reason, and it has to do with the changing in the depth of the ocean, in the depth of the beach, right? Change the depth of the water, okay, nearby the beach, nearby the beach. In the open ocean, we do not have this effect because the depth of the water is more or less constant, okay? So instead of seeing the wave breaking up into that white foam, you just see the regular wavy pattern, okay, with waves going up and down, but never breaking down, never breaking, okay? More or less constant. So it has to do with that. Whatever derivation we do here for the ocean wave can be applied also to the sound wave. Can also be applied to the sound wave. And the way it goes is like that. Visualize your wave in the high seas, okay? And there is a source producing this wave, maybe an earthquake, a point source producing an earthquake, generating an earthquake, and that earthquake generates this wave, a circular wave. It's going to be circular wave if the point source, if you have a point source, okay? If there's something vibrating there at the bottom of the sea, you are going to produce a wavy phenomenon, a wavy effect. And that wave is going to have a given wavelength. And that wave is going to propagate with a velocity that depends on the characteristic of the water, okay? So here we go, and now we have an observer here. The captain in a boat, he's anchored to the seafloor. And because of that, the velocity of the observer with respect to the source, O for observer, S for the source of the wave, is going to be equal to 0. So think about that. You know, the captain is there at the boat and he wants to measure the period of the wave. It's not difficult to do that. His boat is anchored to the seafloor. When the wave passes by, his ship is gonna move upwards to the crest of the wave. His ship is floating, and then it's gonna move downwards to the valley and upwards again. Okay? Gonna keep on doing that. The captain can can determine the period of the wave just by using a timepiece. Can you picture that? Picture yourself in the high seas with your boat. We have a timepiece. You've seen that bobbing up and down of your ship. And then, you don't have anything to do. Let's do something fun. Let's find out what's the period of this wave that's coming by us. And let's see if the period changes, right? That's one type of very simple experiment that you can do to fill up your time if you're bored, right? So, and just by observing that, just by making this observation, the captain can determine what's going to be the period of the wave. The period of the wave and consequently the frequency of the wave. Okay? So let's write it down. We can write it down right in here in our notes. Okay? Or less constant, okay? This treatment, let's put it this way. This treatment of the ocean wave can be extended to that of a sound wave as well. Even though the phenomena are, even though you have a wave propagating different media, even though we have the wave propagating in different media, okay? So, suppose you are in the high seas with your ship, okay, anchored to the seafloor. Anchored to the seafloor. Somewhere nearby you, you have a source of vibration in the seafloor, on the seafloor. I'm not going to go into the details what the source of vibration is, okay? Maybe it's a minor earthquake. It is a minor earthquake that's producing a vibration which produces a wave. It doesn't matter what the source is. Just think that there is a source of this wave. Okay? Because of the resulting wave, okay? You observe that your ship bobs up and down as time goes by. That's the situation. Realizing that you can, right, measure the period of this wave and curious whether the period is constant or not, right? And curious whether this period is constant or not. You get your timepiece. And measure how long it takes for the crest of the wave of each consecutive wave, how long it takes for each consecutive crest, right? For each consecutive crest to go by you. Let's say this period is one, and let us say this period is 1 second. 1 second, no, sorry, 1 minute. Okay. Then you get your drone, right? Then you have the period. You do not have the speed of the wave. You do not have the wavelength of the wave, but you can measure the wavelengths of your wave if you get a drone, right? And observe the crests from both, okay? Then let us say you also want to measure the wavelengths of this wave. Then let's take this one out. That now you want to measure the wavelengths of this wave. Then you get your drone, okay, with a camera and image the waves from above using your ship as a reference for lengths, right? You estimate, you're not making a precise measurement because the drone has to fly up, right? And you're going to use your ship as a ruler to estimate the size of the wave, right? The size, not the size of the wave, but the distance between each crest of the wave. Using your ship as a reference for length, or as a ruler, right? You estimate that the wavelengths of the wave is 10 meters. Remember, estimate. You're not making a precise measurement, but whatever measurement you're making is still very useful. It's an estimate. It's better than having nothing. Now, at this point, now at this point, you already have two important parameters of your wave. It's period and wavelengths. Period and wavelengths. And now you can find, right, the wave's speed. So let's go get our equations. Here you go, one equation here. Overshoot it here. D is going to be equal to lambda divided by T. Lambda divided by T. This is a very simple measurement that you can make, right? See how simple some measurements can be made. You know, if you go ahead and substitute the numeric values that you measured, you get something like that, 1 divided by 6 meters per second, which is 0.15 meters per second, approximately 0.15. And since you already have the period of the wave, you can also measure the frequency of the wave, which is the inverse of the period, 1 divided by 60 hertz. That's going to be 0.015. Okay. Approximately 0.015 hertz. So whenever you are at rest, think of those experiments, right? The experiment between quotes, right? Think of those experiments as thought experiments. They're very useful. Remember that Einstein, he made this marvelous discovery just by performing thought experiments. He was not there in the lab finding out ways to come up with his laws of relativity, especially that law of the speed of the light, right? The speed of the light is the same no matter what referential you are, no matter what inertial referential you are. So that's what we're doing too. We're doing some thought experiments here, aided by some drawings that we're making as well. So, conclusion, right? Conclusion. Whenever you are at rest, you measure a frequency. Let's make sure that the number is right. 1 divided by 60. 1 divided by 60. Yeah, 0.0160. Oh, 1666. Here you go. 0.01666. And here is going to be 0.1666. Conclusion, whenever you are at rest, you measure a frequency of 160 hertz. Okay. Now, you want to do something else. You want to do something else. You want to move your boat towards the position, towards the perceived position of the wave source. Okay, you perceive that the source of the wave is somewhere in a given direction, right? If the wave is coming towards you and you want to go towards the source of the wave, you have to move against the wave. You have to move against the direction of the wave, right? Or against, or towards a direction against the incoming waves. Okay? And so it looks like something like that. Here's your observer, okay? And you're moving towards a position against the direction of the incoming wave. Take out the anchor, right? Raise your anchor. And then you perform the same experiment, right? You perform the same experiment. You get your timepiece, Watch it when the wave comes by. Watch it when your ship bobs up and down and up. Measure this period. I was already in a motorboat in a situation like that. It was really scary sometimes, but it was safe. The guy knew what he was doing. Okay, when every time the wave would come, the motorboat would move up, bang, bang, bang. It was really something. I remember that. It was a long time ago, back in 1985. I was in Puerto Rico at that time. But I didn't know much about Doppler effects at that time, so I didn't bother measuring the period of the wave, right? And now what's going to happen? The wave is still coming towards you, but you're going to perceive a different period. You're going to perceive a different period because you're moving towards the source. Okay? So let's say you're the captain. You're moving at 10 meters per second. It's not bad. 10 times the speed, your walking speed, right? 10 to 20 times. 10 meters per second is going to be what? Let's do the math here. 10 meters per second would be 36 kilometers per hour divided by 1.6, 22 miles per hour. Not bad, right? 22 miles per hour. Now you want to do something else. You want to move your boat towards the perceived position of the wave source or towards a direction against the incoming wave. You raise anchor, right? You raise anchor. Turn on the motor of your boat and start moving. And start moving. How do we find out the perceived period of the wave, right? Well, just remember that the velocity is lambda over t, but now this t is going to be different. The wavelength is not going to change. The wavelength is not going to change because you still have your drone, right? Flying above you. Your drone is taking a picture of the waves, and the drone will be able to estimate the distance between the crests of the waves. And now, what's going to happen? Your speed now is going to be what? Your speed is going to be, I'm going to put V prime now because it's different from the other one. Okay. Your speed is going to be the speed of the observer plus the speed of the wave. Okay. I'm going to put O instead of not. O for observer. We solve this equation for the new period. Okay. And you get something that's going to be less than the original period. Okay, you can do, in this case, you can do both experimentally, right? You can time the period, and on the top of that, you can also figure out if your theory makes sense, right? You use the velocity that you calculated whenever you were at rest, whenever you're anchored. You have a device that tells you what your speed with respect to the to the bottom of the sea, and you can find out whether this theory makes sense or not, whether your theory works or not. Okay. Now you have two ways of finding out whether you're doing things. Well, you have two ways of finding out what's going to be the period of the wave, right? Both experimentally and theoretically. Here's your theory. And we can go ahead and, calculate, right? Calculate the new period. The wavelength is 10 meters because it's still the same wave. The velocity that you are moving is 10 meters per second. 10 meters per second, right? And the velocity of the wave we saw before is 0.167, right? Let's round it up to 1.67. This guy is no longer here. Because this number, is almost 100 times less than this one, we can approximate this equation. So you don't have to keep on doing calculations, right? Say 10 meters divided by 10 meters per second is going to be around 10 seconds. The period is going to be approximately 10 seconds. Let's see, the period, okay, this period is going to be greater, not less, but it's going to be greater than the previous one. Right now, it's not 10 seconds, sorry, it's 1 second. Oh, it's going to be less than the previous one, right? The previous period was what? 60 seconds, was 1 minute. Yeah, okay. Can you picture now? That's what and then what's going to happen to the frequency? Now we can come up with the frequency as well. It's going to be a different frequency. Okay. Start moving. Find the new frequency f prime. 8044. Okay, the new frequency f prime is going to be 1 hertz. Again, it's going to be an approximation, right? Hertz. And that's going to be f prime. Oops. That's my f prime, right? So this f prime is going to be what compared to the other one? F is 0.016 hertz. This one is 1 hertz. So f prime is greater than f. That's what we call, this is what we call a blue shift of the frequency. Why is it called blue shift? There's a reason we call blue shift, right? I wrote that down here. If I have to write, I will, even if I wrote before, I'm going to write it again. This is what we call blue shift. Why blue shift? Why blue shift? Huh? Because in the electromagnetic spectrum, the blue color has a higher frequency compared to the other colors. Okay, so we have this shift in the frequency of the wave just by putting the boat moving with respect to the source. If we are going to, so let's here is the like that. That's my new equation that you have to keep in mind. Okay, and then you can do all the way around too. What if you're moving away? What if you move away from the source of the wave, right? What if you move away from the source of the wave? Okay, you get all the way around. You know, let's put here towards. I'm gonna F prime towards the wave. If you're moving away, it's gonna be something like that. And the moving away is going to be less than the regular frequency, which, by the way, is more than is less than the frequency when you're moving towards. Okay. In this last case, we have a redshift, a shift to lower frequencies, or a shift to lower frequencies. Okay. And which is illustrated. I don't have it here, no, unfortunately. But just change the direction of motion here of this one, right? Here you go. That's a redshift. The period of the wave is going to be longer because you're going to be moving away from the waves. And you get the so-called redshift. Okay. Save this guy. Then we're going to do something else. What time is that? 8:50. Yeah, let's go for our break first, right? Before you go, we do something else. Then next, see what we did. We did the following. One, found the period of a wave whenever you are at rest with respect to the wave. We did the following. Found the period of the wave whenever you are moving towards the wave. You are moving towards the wave. Found the period of a wave whenever you're moving away from the wave. That's gonna be blue shift. found the period, right? Period increases, so the period increases, period decreases, right? And frequency increases, blue shift. And then we can move, whenever you are moving away from the wave, period increases, frequency decreases, red shift. In the next step, let's see, the next step, the observer will be at rest, and the source is going to move towards or away from, towards or away from the observer. Okay? And let's see if it changes anything from the wave right here. But before we do that, let's take attendance. Interesting. And how many students do we have? Hopefully I didn't miss any messages from you. Right? We have only 10 students here today. I guess everybody is taking advantage of tomorrow's holiday, right? Today is the 3rd of July. Second and 3rd. Yeah, July 3rd. Sydney? Are you there,
I'm
Sydney?
here, Professor.
Okay, thank you.
Good morning.
Oh, by the way, I corrected your first lab report. Okay, I'm going to talk about that. Maybe I should talk during the break, but just check your folder right here. Here's group 1, right? Group 1, here you go. You are going to need this file here and this folder here, okay? I will give you directions on how to see your correction. It's an HTML file and the folder. They both must be downloaded to your hard drive and consulted, you know, they also must be in the same folder. You gotta download, but I'll explain that maybe at the beginning of the lab, right? Here's group 1. Let's take a look at group 2. Group 2 here, right? HTML file. Group 3, here you go, HTML file right here. Group 4, HTML files. Sometimes it's lost, right? Watch out. And group 5, folder and HTML file. Okay, let's continue here with the attendance. Amy. Hello, Amy. Amy is here, but it looks like she's away from the computer. Andy? I don't see Andy here. Next is Alex Hernandez. Hello, Alex. Looks like Alex is away from the computer too. Okay, one more startup. Oh, good. Oh, Alex here. Good. Thank you, Alex. Next, Basil.
I'm here, Professor.
Thank you. Jeshwan.
I'm here, Professor.
Thank you. Zaid. Thank you. Sumana. I don't see Sumana here. Amy, are you there, Amy? Are you back? Okay, Alisa,
Here.
thank you. Karthika? And Karthika is not here. Mary? Mary is not here. Raymond Silverman? Thank you, Raymond. Ashley Tai?
Here.
Thank you. Kirakus? I don't see Kirakus. Alexis Madrigal Valle? Alexis is not here. Parth, okay, Parth must have dropped. And I should have here 9. Okay. And okay. Amy, are you back, Amy? Okay, good. So let's take our break now. The nose is here. Let's break from 9 a.m. to 9:15 a.m. Any questions before we go? Good. So I see you in 15 minutes. Oh, sorry, did parts drop? I think so, Sartak. I think so. I didn't check my okay. back here. Let's see. Anybody else come in? Let's see. Okay, Alexis is here, right? Hi, Alexis.
Hello, Professor.
Okay, so I'm giving you a tendency here. Invite me back to her phone, to her computer. Looks like we have one more student. Let's see. Who was not called? Sumani is here. No. Karsika? Karsika is not here. Mary, are you there, Mary? No. Kirakus. Okay, so what's going on here? 11. Okay, good. We're in good shape. Okay, let's go back what we were doing. Now, what happens whenever the source is moving, right? So we did here the case in which the observer is moving away from the source and towards the source. And then there's also the case in which the source can be moving towards the observer. Okay? And that's going to be the next step here that you're going to take. And let's see what happens. Let's see what happens. I have some nice simulations here. Let me take a few minutes to see if I can find. I have simulations on that, okay? I'm going to pause the recording a little bit here, so take too long, right? And I'm sharing the screen right now. Sound wave. Let's look at this one here. Sound wave. Maybe that's the one. Where in the Google Drive can we find our lab grades? Oh, your lab. Yeah, I'm gonna talk about that at the beginning of the lab, 12 noon. Okay. So just hang in there. Let's wait for everybody to come in, Raymond, and then I will tell everybody how to access their grades there. Okay. Standing wave interference. Let's see, moving source. I have moving source here. Okay, you remember that, right? We have this one, we have this one. Let's see, interference, standing wave, beat. We have the moving source case here, but yeah. Okay, and then we have the relativistic Doppler, right? We're doing that. Don't forget, we're gonna have this chapter, these two sections in the third exam. No, it's not the third exam. Right, it's gonna be on the final exam. Let's start talking about the exam too, right? So we had our second exam just last week, and whatever we managed to cover up to last week, and what we covered was exam 3 so far, right? Right in here. Here you go. Exam 35.12345, 36.12345. And I want also take right here 35. Yeah. 0.12345. Yeah, we did that. 36.1234 and 5. We didn't do 6 and 7. Okay. Although 7 is very similar to that. Okay, but I want to cover that. And what else we call? Oh, we start covering relativity, right? We started covering relativity. Okay, so what I'm going to ask from you, yeah, for relativity, okay, there won't be nothing on relativity, okay? Let's leave relativity for the final exam. Yeah, let's do it. Let's leave just those 2 chapters for exam 3 plus lab 1, okay? Let's do it this way. Everything else, okay, final exam is going to be cumulative, right? Everything in the semester, but okay, the chapters that did not show up in the partial exam will make up 30 to, let's say, 60% of the final exam. Okay, man, it's going fast, right? Next week is going to be the last week of the summer. Yeah, see that? Last class is going to be Thursday 13th. So it's going to be next week. We have a little bit more than 1 week and a half, well, a little bit more than 1 week. We have 1 week and a half left. Those courses are crazy. They're really crazy. But let's take a look here if I can. Moving source, yeah. And let's start writing here. Okay. Okay, so how does it work? We start with the source, okay? With the source here at this instant of time 0. The source is starting to emit its wave. It's going to be a circular wave. And let's take a look. Yeah, here you go. But the source is also moving, okay? In this specific case, would be the supersonic situation. Let me change. Let's see if I can change the speed of the source. If I cannot change the speed of the source, I'll have to check the other simulations. Maybe this one. Let's see, standing wave, moving source. Okay, this one. We want this one. Yeah. And that's, the type of simulation. I did the simulation when I first taught this course. It was really fun to do that. Okay, so the source is moving. The observer is somewhere here. Let's see what happens, right? The source right in here is already moving the source, but we're taking a snapshot at the moment that the wavefront, the first wavefront is being emitted, okay? A little bit later, the wavefront has propagated away from the center, from the point where the source was located, okay? Now note that the source has moved from the origin of the coordinate, okay? But the wavefront is still centered at the origin, at the previous position of the source. Seconds, 2 seconds now. Okay, see what's happening? The wavefront is centered at the origin, but because the source is moving, it is off the center of the wave, right? 3 seconds, yeah. The wavefront is moving away, propagating with that old center that it emitted. And now start thinking what's gonna happen when the second wavefront means the crest of the wave. That's what I mean by wavefront. Okay, the crest of the wave. We still have waves here. We have we just don't, I just didn't picture it, okay? Because I'm picturing only the crest of the wave here. Here you go. 4 seconds, 5 seconds, 6 seconds. Eventually, we're gonna have our second wave front here. 8 seconds, 9 seconds. It looks like I gotta go faster in time, right? 12 seconds. Oh yeah, here you go. So let's go 11 seconds. Let's go back in time, right? 10 seconds is here. Okay, so in sometime between 10 and 11 seconds, the source, we have the second crest of the wave, okay? So anywhere, anytime between 10 and 10 and a half seconds, maybe 10.3 seconds, let's see. Yeah, 10.2, let's try 10.2, yeah, 10.1, actually it's 10 seconds, yeah. Actually it's 10 seconds, let's see here. Yeah, you can see, right? At 10 seconds, we cannot see the wavefront, but at 10.05 seconds, yes, we can see the crest, the second crest of the wave. Okay. So 11, and so the second crest of the wave start to propagate away, right? And maybe the other crest is going to occur at 20 seconds, every 10 seconds. Let's see. Now, yeah, that's right. So I put the period of this wave as being 10 seconds. I'm illustrating the period of this wave as 10 seconds. We can clearly see the bluish dot there. If we move to 22 seconds, here you go. Do you see how a wave is formed? A sound, you know, it can be, how a wave is formed whenever the source is moving. It can be an ambulance with a siren. Okay, those are the crests of the sound wave, for instance, or the crests of a water wave too. It can be a ship, right? It can be a motorboat with an oscillator banging up and down in the water. It can be something like that. Okay, if the water is clean, there is no other disturbance from other sources there in the lake or in the sea, you would be seeing something like that. Okay, 24, 26, 28, let's see, 30. So we should have another source here, another, no, let's see, 30.1. Yeah, okay, I didn't put another one, just too much work. Just too much work. Let's see, 32. Yeah, that's right. I didn't put the force wavefront. So look what's happening here. Look at what's happening here. The wavelengths on the side of the source is shrinking. Okay? Closer to the side of the source is shrinking, right? And in the way, on its wake, what happens to the wavelengths? The wavelengths increases. Okay? That's what we have when we have a source moving like that. If you are an observer sitting right in here at this spot, don't let yourself be run down by the ambulance, right? You are going to perceive a shorter wavelengths. Shorter wavelengths means what? Means higher frequency, right? Lower, higher frequency. If you are an observer sitting down behind in the wake of the source, right? You're going to perceive a longer wavelength. A longer wavelength. Since the sound propagates, since the speed of the sound has to be 330 meters per second, so the frequency must make up for the longer wavelength. So you must have a lower frequency here. Higher wavelength, greater wavelength, lower frequency. Shorter wavelength, higher frequency. This simple drawing explains the Doppler effect. That's what this that's what this drawing is all about. Okay. Let's play the movie again. I'm going to move back in time. There you go. I'm moving back in time and 0 seconds, right? I'm gonna do the following. I'm gonna redo that again, okay? And then I'm gonna play the movie. Every two seconds, 10, right? And don't forget the second wave front is occurring right now at t equal to 10 seconds. 12, 14, 16, 18, 20, 22, third wave front, 24, 26, 28, and then we are supposed to have another wave front here, but I didn't draw that one because it was too much work. And now we can go back in time. Okay, and play the movie again. Here you go. Source is moving. So picture your ambulance coming towards you. If you pay close enough attention, you're going to see that the frequency of the sound wave changes as the ambulance passes by you. Okay? And the drawing, the static drawing, looks just like that. The source moving towards the observer, right? Here you go. I didn't put the observer there in my simulation. The ever expanding wave, the other wave front, which is the crest, nothing but the crest, right? And here is the new wavelengths, the compressed wavelengths. That's how you should picture it. And then we have to start making sense mathematically of these wavelengths if we want to understand the Doppler effect whenever the source is moving with a moving source. We gotta do that before we get into the relativistic Doppler effect. Here you go. That's my drawing, right? And here is another way to look at the wavelengths. The source is about to emit another wave front. Okay. And the tricky is right in here. The distance of the source from here to here is going to be Vs times the period of the wave, right? So don't forget, the source is about to emit its second crest, its second wave front. But let's not forget that we also have lambda prime, which is the Doppler shifted wavelengths of the source. from here to here, from here to here, is the regular wavelength of the source with no shifting due to the Doppler effect. Okay? So now we can write that down. So I'm going to notes right here. With a moving source, the treatment is a little bit different. A little bit different. Is different. Not a little bit different, but is different. The treatment is different. In this case, the waves are emitted off center. The wave fronts, not the wave, the crests, right? Each consecutive crest, each consecutive crest are off center. Are off the center. Off the center of the previous one, of the previous crest, right? Like that. With a source, with a moving source, speed v sub s, right? I'm gonna put v sub s here. We need to document the speed of the source. The treatment is different. The treatment is different. In this case, each consecutive crest are off center. Is, not are, is off center of the previous crest. Okay. Looking carefully at the drawing provided, okay, we can see that there are regions where the wavelength is compressed in front of the source. And elongated behind the source. And then you have everything else in between, right? Elongated, right? Behind the source. And everything else in between. Going back here. Not here. No. In the simulation. Right in here. Here, the way you have one wavelength. Here you have another wavelength, right? Here we have another wavelength, and the longest possible wavelength in this direction. Here is one wavelength, here's the other wavelength, here's the other wavelength. And we can find out precisely, we can come up with a precise equation of how these wavelengths change. And you can picture that from here, from this drawing. Lambda prime plus VST is equal to the wavelength, if the source was to be at rest. So let's go there. Okay. Lambda. Lambda means the wavelengths with the source at rest. Lambda prime, the wavelength in front of the source, and the velocity of the source times the period of the wave. Right? Like that. Then we can go the next step. We can write that down in terms of the frequency as well. This one in general, we know this value here. This wavelengths, the wavelength of the source at rest. So we have to write and in general, we do not know. So we have to write the known in terms of the known. Okay, the frequency of the source is going to be given in terms of these wavelengths and the speed of the sound, right? And the velocity of the source can be controlled. So we have this relationship here. And then this relationship here. Lambda prime equal like that. Let's not forget that there is a relationship for the, you know, it's like that, right? The velocity of the sound is going to be given by the wavelengths times the frequency. Here's velocity of the sound, here's velocity of the source, not sound, okay? Don't mistake yourself by the velocity of the sound. And now that I found what lambda prime is, I can substitute that right here. How did I put lambda prime here? It's supposed to be lambda prime. And yeah, gonna be, and then I'm going to write the frequency in terms of the speed of the sound and the new wavelengths. Speed of the sound and the new wavelength. Like that. The new frequency depends on the speed of the source and on the speed of the wave, right? Here is speed of the source, here is the speed of the wave. Let's not forget that. And now I can here write my lambda in terms of the speed of the sound and the original frequency, right? And look what we are getting. These two terms can combine in a single denominator. Okay. Now the frequency, original frequency, can go upstairs. And look what we get. We get this relation, this final relation. Doppler effect. Moving source. That's for the moving source. Okay. Let's not forget, okay. Let's not forget that this term here is greater than 1. Right? Remember, is a positive number minus a positive number. But this number here is equal to this one. Consequently, you are dividing this number for something less than itself. Consequently, it has to be greater than 1. If it is greater than 1, it means that the new frequency is greater than the old frequency. This is also blue shift, right? This is a blue shift as well. This is a blue shift as well. That's in astronomy. That's what they say in astronomy, okay? What if the source is moving away, right? What if the source is moving away? Well, we do something similar, but a similar treatment. I'm not going to do the treatment here, but you can try to figure that out on your own. Okay, just take a look at this drawing, right? This is a wavelength. This is the original wavelength, right? This is this distance is the original wavelength plus VST, right? Original wavelengths and new wavelengths, right? The new wavelengths is going to be VST plus original wavelengths. Unlike the other one that had that negative sign, it's just a change in signs. Since it's just a change in sign, all you end up getting is something like that. And now we have the following. Okay, let's put it away. Let's see, not away, but in the wake, right? Here is in front, right? And now let's put all the equations together. We have 4 equations. Observer moving towards the source and observer moving away from the source. Let's get that. There's a reason why we're doing that. We're doing that because we want to get a single equation. Wake, away, let's see here. Moving observer. Moving source. Okay, let's see, away we go. We can do something else here, right? I didn't do that, I should have done that. this wavelength here is going to be V times F, right? V divided by F. V divided by F. I didn't do that before. V divided, no, wait a minute. V here, oh, V here and F here. V here and F here. And now we have, if you go ahead and put everything together, okay? And then we can have a combination, right? Combination, source and observer moving. We have something like that in table format. Okay? So if you have both the observer and the source moving, we have this case here. Okay? Notice that this equation is the more genetic one whenever the source is moving towards. Well, when they are moving towards each other, right? When they're moving towards each other. If the observer is at rest, then we reduce to this equation. If the source is at rest, we reduce to this equation. Okay? So moving towards each other, moving away from each other. Moving away from each other. Moving towards each other. So we have a plus and minus situation here. Okay? So the situation, if I want to write that down in a more generic format, is going to be like that. F prime is going to be plus and minus, right? And then downstairs, plus and minus. Oops. Oh, it's not plus and minus. It's supposed to be minus and plus, right? Minus. When this one upstairs is positive, the other one must be negative. When this one down upstairs is negative, this one must be positive. Okay. So plus and minus upstairs means moving towards. Okay, like that. Plus and minus upstairs means moving towards each other. Plus and minus upstairs and minus minus and plus downstairs mean moving towards each other. And then, no, wait a minute. No, that's not the way to do it. plus upstairs. The right way would be like that. Plus upstairs and minus downstairs, right? Mean moving towards each other. And then the opposite is true. Minus upstairs. It's not difficult to memorize, right? Plus downstairs means moving away from each other. Right? That's easy to remember, right? If the plus is upstairs, they're moving away, that they're moving towards each other. Their relative speed is increasing, right? Their relative speed is increasing. And if you have plus upstairs and you must have the minus up downstairs. Minus upstairs means that their relative speed is going down. Consequently, they must be moving away from each other. Okay, and let's not forget, let's take a look at the section number. 17, go here. 17.7, and now we're going to do 17.8. Let's go for another 15 minutes. Okay. So, and lab 1. Okay. We're covering 17. We are covering 17.7, chapter 17.7. Chapter 17.7 and 17.8. Ten o'clock. And now we can start talking about shockwaves. Let's take a look at our simulation, right? There you go. Did you notice that the speed of the source is less than the speed of the wave? Did you notice that? And also, keep in mind, if you're dealing with the sound, a sound wave, each of those crests means that we have a region of higher pressure. Okay? High pressure, high pressure, high pressure. That's what we have here. What if the source is moving faster than the wave? Believe it or not, we see that every time that we go, that we watch those ships navigating there at the beach, right? Not at the beach, but in the marina. We see that all the time. And I'm going to explain that. Let's start with a t equal to 0, right? T equal to 0. And then let's start our simulation. Okay, at this very moment, the source is emitting a crest, right? You'll be able to see the crest. If I move a little bit, no, let's see. Yeah, okay, yeah. 0.5 here, let's see. Yeah, the crest is right here behind the source. Okay. So here you go, let's start. 1 second, 2 seconds, we see that the source is ahead of the wave. 5 seconds, 7 seconds, 8 seconds. Let's go faster now. Otherwise, it's going to take forever, right? At this very moment, the source is emitting another wave front, a crest. Here you go. And he go and is leaving the wave behind. 18, 20. Here go. Here's another one coming. You don't see yet, but it is coming. Here go. 22 is already behind. 24, 26, 28. And then what do we have here? We have here a line that makes a tangent to each one of those crests. Okay. Not only that, we have also a superposition of these waves, a constructive superposition of these waves. And by the way, there is a mathematical way of treating what you see right here. Okay, let's go back here. Okay, right here. Right here. The distance from here to here is the distance of the source, which is the speed of the source times t. Okay. And the distance from here to here is the distance covered by the first crest of the wave. The first one that was emitted at time t equal to 0. Again, I'm assuming that the source is moving with constant velocity, okay? I'm assuming that the source is moving with constant velocity. And I've got to come up with something else here so you can understand better, right? I need this hypotenuse here. So you can see that we have an angle right here. Here is VT, right? Here is VST. Here is VST. So we can relate VT with VST. And what is going to be according to this drawing? Right angle triangle. The line, this line that you see here is going to be tangent to this circle. And tangent to this other circle, and tangent to this other circle. Looking at the drawing, right? Okay, so shock waves, here you go. If a source is moving faster than the speed of the wave, of its wave, comma, if that source then we have a very interesting phenomenon. That of a shock wave. Looking at the illustration, we find that there is a relationship between the speed of the source and the speed of the wave. And the relationship is something like the following. Sine of theta is equal to velocity of the wave divided by velocity of the source. Okay, I'm going to even put here, I'm going to emphasize that the velocity of the wave. So you don't mix up, this one is velocity of the sound, okay? It's velocity of the wave, velocity of the source. It doesn't have to be sound. It can be any other wave. any other type of wave. And there are some neat pictures that we can take out there in real life. Speed of the sound, let's get that, supersonic. We go, okay. Here is the case in which the velocity of the source is the same velocity as this wave, okay? I didn't do that, but it's the same. But then, if that's the case that I did, remember that these waves are being emitted very quickly, right? For instance, in the case of the sound, we are talking about the frequencies that go from 20 hertz to 20,000 hertz, right? So whatever drawing that I made here doesn't represent reality at all much, right? In reality, you have a bunch of waves here. In a single second, you can a given source can emit up to 20,000 wave fronts. I'm making only 3 wave fronts here. In a way, I am exaggerating on the other way, so you can understand what's happening here in real life. Here is a little bit more realistic, what you have in your drawings, a little bit more realistic. Note that now that we have all those wave fronts even closer to each other, and all those wave fronts, they are forming a region of high pressure. They're forming a region of constructive interference in which the sound ends up being louder. The amplitude ends up being louder. That's why we have what we call the sonic boom whenever a supersonic aircraft passed by us. It just happened recently, right? That some fighter jets had to break the sound barrier over populated area. They're nearby Washington, D.C. They do that. They're not allowed to do that. If you're flying a supersonic airplane, you're not allowed to fly supersonic above populated areas because it produces a sonic boom that can damage glass, it can crack your glass, right? And also cause people to think that there is some explosions occurring, okay? So if you are flying a supersonic airplane, you can break the sound barrier only above areas that are not populated, unpopulated areas over the ocean, where nobody can hear your big noise, right? However, under certain circumstances, like in the case of emergency, in an emergency, pilots are allowed to break the sound barrier over populated areas, and that happened recently. That happened like in the case of, maybe you watched the news recently, right? There was this case of this airplane that was flying over restricted airspace in Washington, D.C. And the government had to scramble its supersonic aircraft to intercept this airplane. It can be some sort of a terrorist attack, right? Someone trying to crash the airplane in the White House, right? Or in the Capitol, like it happened in 9/11, right? So they have to scramble the jet. And under those circumstances, which is an emergency, yeah, you're allowed to break the sound barrier under populated areas. Yeah, you're allowed. But those things don't happen all the time, okay? I recall only 2 instances in which something like that happened in the United States, okay? This one that happened recently, and then several years ago as well, in which a pilot that was flying a Learjet, they lost pressure in the cabin, and the pilot, everybody that was inside the airplane, they lost conscious, right? And the airplane just started flying by itself until it crashed into the ocean. In this circumstance, apparently that's exactly what happened recently. Okay, and then there was another case back in Brazil. Okay, I was here in Brazil when that happened. It was during the Falkland War between Argentina and the United Kingdom. I was an undergraduate student at that time, okay? So I was there in Rio in my, the university, the Federal University of Rio de Janeiro, and I was the student dorm. And then suddenly I heard this big sonic boom. I didn't know what was that, right? But back in Falkland, here you go, Falklands War, here you go, Falkland War. Argentina invaded a United Kingdom territory that's called the Falkland Islands, okay? And for several years, Argentina was claiming those islands as part of Argentina. And they still claim this island as territory of Argentina. And they never got into an agreement with the United Kingdom. And then it was in 1982, okay? 1982, the Argentinian government, which was a fascist government, right? If you watch the movie, The Iron Lady, she mentions that, right? Iron Lady was Margaret Thatcher. And the Argentinian government, which was a dictatorship at that time, was hanging by a thread. And in order to stay in the power, they decided to invade the Falkland Islands and get all the Argentinian people behind the dictatorship, right? Their dictatorship. And like it always happened, right? Every time that we hear the drums of war, drum beats of war, the population stay behind the government, and the government survived because it was a dictatorship. But it was a big mistake because Argentina couldn't fight a war against a superpower like the United Kingdom, which, by the way, had NATO behind it. Okay, during that war in 1982, I was there in Brazil in the dorm, and I heard that sonic boom. What happened? Brazil is next to Argentina, okay? And what happened at that time, and by the way, at that time, Brazil was supporting Argentina claims of the Malvinas Island, right? The British called the Falkland Island, the Argentinians call it the Malvinas Island. And so what happened? What happened was very simple. One of the United Kingdom airplane had a mechanical malfunction, and they had to enter Brazilian airspace. Okay? And think about that. We are talking about a warplane carrying some weapons into Brazilian territory, and it was an emergency on the part of the United Kingdom pilot. And now what the Brazilian government had to do has to send out, had to scramble their jets, right? And the Brazilian jets had to break the sound barrier over populated areas and escorted the British plane that entered the Brazilian airspace, Brazilian territory, Brazilian sovereign airspace. And they escorted the plane until the international airport there in Rio de Janeiro. I went there to the international airport and I saw the bomber, the United Kingdom bomber. The Brazilian government dismantled all the weapons from the airplane, right? And kept the weapons and returned the airplane to the British. According to international law, that's exactly what the Brazilian government had to do. They had to take away the weapons from the airplane and then return the airplane. The Argentinian government was begging the Brazilian government to return the airplane to Argentina, so they could keep it as a trophy, right? But the Brazilian government, even though they were supporting the Argentinian government in that war, they ended up fulfilling, of course, following the proper international rules. 1982. That was in 1982. I was an undergraduate student there, here in Brazil, in Rio de Janeiro. Okay. And 1020, right? Oh, let's see if I can show you an actual picture. This is not an actual picture. This is just an illustration. Here you go. Here's an illustration. Here's an actual picture of the sonic boom. Okay, we have a region of high pressure. What you see right here is a cone. There is a cone here, another cone there, right? Shock waves produced by the wings of a Navy FA-18 jet. The shock waves are visible because the sudden decrease in air pressure in them caused water molecules in the air to condense. Okay, and you can also take pictures like that in wind tunnels showing that cone. Let's see if we can see here. Unfortunately, they don't have it here. Yeah, let's take a look at the internet. As cone, sonic cone, sonic cone. Let's see. Okay, that's one here. Okay, and but that's not the one I want. Sonic cone, maybe here. If you're in the wind tunnel and you are simulating, right? Supersonic speed, okay, you don't have it here. Scientists always take a picture of that, and you can clearly see in sonic cone, Wikipedia, vapor cone, sonic boom. Let's try this one here. Okay, same illustration that I made. See that? Same illustration that I made. Here you go. Here's the sonic, the shock wave, the conical shock wave. They don't have it here either. Let's see, supersonic, supersonic track, supersonic boom. Let's try that. Supersonic speed. Let's try this one. No. I will find it. If I take too long to find it, let's see. That's the type of thing. And by the way, when you see this cone here, you know, that angle that I showed to you can be calculated from the angle of the cone, right? Is the what you see here, theta is the angle that the cone makes with the horizontal. So this cone here can be calculated, the angle of this cone here can be calculated by using the speed of the aircraft and the speed of the sound. Okay, if the speed is transonic, if the speed of the airplane is transonic, now suppose that the airplane here is, and I'm gonna put it in the simulation. Here I did supersonic, right? What if the velocity is not supersonic, but the velocity is exactly the velocity of the sound? You don't have, you get a cone in which the regions of high pressure makes an angle of 90 degrees with the horizontal, okay? The faster the airplane here, the faster the airplane flies, supersonic, the more pronounced the cone is. And it slows down. All that region of high pressure is going to be a little bit more blunt. Let's see if I can get it. Let me. I wanna change the speed here in my simulation. Not this one, maybe the other. See if I have a way to source. Yeah, it doesn't look like I can't find how to change the speed. Oh, here in my simulation. Okay, must be here. 1.5. Yeah, okay. So let's try here. Must be this one here. I'm gonna put it equal to the speed of the sound. Okay. Okay, now do you see that the source is right at the edge of the wave, right? And this one, let's see here. Let's see if it works. I hope I made the right change here. 0. Right. 2. Yeah. 4. At least the first wave is right there, the right position. Okay. 10. Now let's see if the second wave is going to be at the right. Oh yeah, the second wave is not. So I have to make an adjustment right in here. The problem is M2. Okay, 15. Huh. Why 15? Must be here. Yeah, yeah, see, should be 10. I hope so. Hopefully I'm not screwing up with the simulation. Okay, yeah, I must be here. Yeah, okay, and the other one too. Instead of 30, it's supposed to be 20. I gotta make this simulations more user-friendly so I don't struggle with it in a situation like that. What happened? Oh yeah, because we didn't get my, okay, let's go. 20, 14, 16, 16, 18, 20, 20. Here, 22, see that? And now your sine of the, your angle here is not gonna be, it's going to be 90 degrees. The tangent to both waves, circular waves, is going to be here at 90 degrees. Okay? That's what I want to show you. And let's see again, see if I can find those pictures that we take in the wind tunnels, supersonic wind tunnels. Let's try that. Supersonic wind tunnel. Oh, yeah, let's see. Streaming often used to capture image of glass when shock waves in supersonic wind. Okay, so it should be something like that. See that? Chilean photography is often used to capture image of gas flow and shock waves in supersonic wind tunnels. Do you see that? You have a very sharp region here, almost showing the shock wave. If you go ahead and measure this angle of this cone, you can estimate what's going to be the speed that this shock wave was formed. Okay, let's see if we have another one. No, we don't. Okay, that's one example, but we should be able to find others. Supersonic wind tunnel, let's say supersonic tunnel. Supersonic speed, okay, let's try supersonic speed here. Supersonic speed limit. Supersonic speed. Well, another example, yeah, I for some reason I'm not finding, but another example that I can give you about that shock wave, not just with airplanes, but also with ships, okay? Also with ships. If you have a boat, sailing a boat over water, have you ever seen that triangular shape that's forming in the water as a boat's passing by? Okay, that's a shock wave. That's a shock wave that the boat is leaving behind its wake. Shock wave by a boat, huh? Shock wave by a boat. Let's try this one. Shock wave boats. Let's see. Shock wave, premium suspension. No, shock wave. And that's very easy to see. Okay, if you have, oh, right in here. Yeah, see what you see here behind is exactly the same phenomenon. Okay, here's the shock wave that the boat is leaving behind, is leaving on its wake. And how those shock waves are formed? Well, very simple. The speed of the boat is higher than the speed of the wave in the water. That's why they form those waves. This one, another one. Here you go. Everything that this is a shock wave here of the boat. This shock wave is formed because the speed of the boat is faster than the speed of the wave of the water in the water. Okay, another example of a shock wave. Every time, let's write it down. Every time that you have a source that is moving faster than the speed of a wave, of its wave, right? Of its wave, of the boat's wave. Of the boat's wave. In the medium, every time that you have a source that's moving faster than the speed of the corresponding, not the boat, but the corresponding wave in the medium, okay? I'm writing the most genetic possible way, comma, the source will leave behind a shock wave. Shock wave in a conical format, right? An airplane, for instance, moving faster than the speed of its corresponding wave. In the medium, the source will leave behind a shock wave in a conical format. For instance, an airplane, and that moving at supersonic speeds in air will form a conical shock wave with an angle given by the above equation. Similarly, a boat that moves faster than the speed of a ocean wave will leave a triangular path on its wake behind it, right? And then you might be able to think of other situations that you have something like that, okay? So 10:31 already, huh? We went above our time here. Any questions? That's what I want to cover. Okay, and if you visualize, if you manage to measure the angle of this shock wave behind the boat, and you know the speed of water waves in the water, you can find out what the speed of the boat is. Same thing for the airplane, okay? Same thing for the airplane. Here's another boat, okay, shock wave. If I find what I'm looking for, I will show you once we come back from break, okay? But there is a nice picture. That picture takes and posts here in the internet showing a projectile, can even be a bullet, okay? A bullet leaving a shock wave behind it. And some people manage to capture that with high-speed cameras. They can, it's not easy to visualize that, but then you need a special equipment. The shockwave formed by a boat is very easy to visualize, it's very easy to see. But in the case of an airplane or bullets, okay, unless you're lucky enough to get the right conditions in the atmosphere to get that nice picture that you saw of the airplane, right? Let's see if I can get that. Yeah. This thing is very rare. You can rarely pick up something like that. You have to have the right atmospheric conditions to have this picture taken, okay? So 10:33, any questions? We are done with this chapter 17. Break from 10:35 to 10:50, okay? 10:50 a.m. And I see you in 15 minutes. Thank you. Okay, I finally found what I wanted. Let's look into shock waves. Okay, and those are real life pictures that you can determine the speed of, for instance, on an object with respect to the speed of the wave in the medium. Here you go. So do you see the cone here formed? That's called Schillerian photograph of an attached shock on a sharp-nosed supersonic body. Okay, and if you go ahead and measure the angle of this cone, you can find out the speed of this airplane. Okay, there are more, right? This one's you can clearly see, right? The cone, sharp-nosed supersonic body, and then there is another one here. Right now, a bullet, supersonic flight, forming this shock wave behind it. Again, if you measure this angle here, you know, the size of this triangle divided by this size, you'll be able to estimate the speed of the bullet in the air. Now, look at this one. This one is even sharper than the other one, right? And shadowgram of shock waves from a supersonic bullet fired from a rifle. The shadowgraph optical technique reveals that the bullet is moving at about Mach number 1.9. What does it gloss? Oh, thank you. Okay. So we got to start all over again. Sorry. Okay, so I found it, right? Let's start all over again. Here you go. Here's shockwave in Wikipedia. That's the photograph, Schillerian photograph of a sharp-nosed supersonic body. Here you go. Here's the shock wave produced by this sharp-nosed object under supersonic flight. If you take the angle that this cone forms, you can estimate what the speed of this object with respect to the sound. Okay? Next, another one. This one too, a bullet, supersonic flight. Look at the trail, right? You take, you can, to find out the speed of this bullet with respect to the sound, all you have to do is to measure this length and divide by this length, right angle triangle, right? Measure this length and divide by this length here. And you get your speed in terms of Mach number. Here we have the same thing. You got shadowgram of shock waves from a supersonic bullet fired from a rifle. The shadowgraph optical technique reveals that the bullet is moving at about Mach number 1.9. Okay, if you go there at home and you measure with your ruler the length of this side of the triangle and the length of this other side, you're going to see that this side here is almost twice as much as this one. I measure it right now. Okay, I'm going to measure. Here's my ruler. I'm getting here 10.5 centimeters. And then on the vertical, I'm getting 5.5. Okay? 10.5 divided by 5.5. Let's do the math. 10.5 divided by 5.5, 1.9. Just like you said. Okay? It comes from that equation that I showed to you. And like I said, it's not just a supersonic flight. It can also be in the water, right? The wave left in the water. I like this video here. He explained nicely. I'm gonna blow up that for you to see it. Here you go. Man of physics. Look here, the wake. Oh gosh, I hate that. See that? The wake waves left by those ducks. Okay? The wake of the wave left by the ducks.
If you
And
wait behind a duck or a kayak or
Yep.
a ship, you might notice two unusual things. First,
by the way, water waves is a little bit more complicated than the shock waves in the air. It's a little bit more complicated, but at least you can get an idea, because it's far easier to visualize something like that than to visualize your shock wave in the air, right? And it's far more familiar to you. Let's play. Let's keep on playing. This guy is going to tell a little bit more than what I have told you.
the wake isn't simple like the perfectly straight shock.
Okay, perfectly straight shock wave. The bullet. Take, this length divided by this length here, and you get the speed of this bullet with respect to the speed of the sound.
Wake of a supersonic projectile is. It's a fascinating feathery ripply pattern. And second, that feathery pattern looks the same. Same angle, same repeating pattern of ripples along the edge, same reverse arcs in the middle. It looks the same regardless of whether it's made by a duck, a kayak, or a ship, even though they're all moving at different speeds and the waves are very different sizes. In this video, we're going to explain exactly where this shape comes from and why it looks the way that it does. Ultimately, it comes down to the surprising physics of water waves. While there's a single speed of light waves and a single speed of sound waves, there is no single speed of water waves. In water,
Did you see the difference? We have just a single speed for light in vacuum, a single speed for sound in air. But in the water, you do not have a single speed. The water waves are a little bit more complicated than light waves and sound waves.
water waves. In water, longer waves travel faster, while shorter waves travel slower, at least for waves that are bigger than a few centimeters. This phenomenon, where different wavelength waves travel at different speeds, is known as dispersion, because waves of different speeds disperse from each other. And
Remember dispersion of light? Same concept, right? This idea of dispersion applies not just to light, but also applies to waves in general. Red color travel at different speeds than blue colors, right?
waves of different speeds disperse from each other, and it makes water waves both interesting and complicated. Like a boat wake. To explain the shape of a boat wake, we'll start by looking at water waves of just a single wavelength and speed. A boat traveling across this simpler water creates a series of circular waves.
Do you see what he's doing here? Exactly what I did for sound waves, right? The same, but he's doing just for a single wavelength of water.
If the water waves are faster than the boat encircle it, but you don't get a wake. If the waves are slower than the boat outruns them, and the circles all add together to create a V-shaped wake. And if the waves are even slower, the boat will outrun them even more, and they'll add together to a narrower V shape. Slower waves make narrower wakes.
Slower waves, what does it mean? Slow compared to what? Slow compared to the speed of the boat, okay? That's what he means. He's doing all the way around, right? I was telling you the speed of the boat with respect to the speed of the wave. Now he's telling you the speed of the wave with respect to the speed of the boat. It's lower waves or faster source, right? leaves a sharper cone.
Faster waves make wider wakes.
Faster waves mean slower speed for the source. Oops.
But we need to remember that water waves are waves. That is, they repeat themselves. So every circular wave is really the first of a series of circular waves. This means that instead of creating just one V-shaped wake, a moving boat creates a train of V-shaped wakes that are each exactly one wavelength apart. The reason a real boat doesn't make straight V-shaped wakes is that a real boat makes waves of many different wavelengths. And because of dispersion, different wavelengths travel at different speeds. The longer ones travel faster, and shorter ones travel slower. Faster waves create wider wakes. And because faster waves also have longer wavelengths, that means wider wakes are further apart. Similarly, slower waves create narrower wakes. And because slower waves also have shorter wavelengths, narrower wakes are closer together. The specifics are determined by water's dispersion relation.
Hey, did you see that the formula is very, in a way, is similar to the equation that we saw for the speed of a wave in a string?
The specifics are determined
Right in here. Square root, see that? G lambda over 2 pi in this case.
by water's dispersion relation. When you add together narrow, closely spaced wakes with wider, more widely spaced wakes, with even wider, even more widely separated wakes, and so on, voila, the shape of a boat wake. Look at the beautiful repeating feathery ripples out on the edge, and the wider repeating arcs inside the wake itself. I find it so cool that you can recreate the shape of a wake just from these lines. If you replace the sharp lines with smoother waves at the appropriate angles and spacings, you get an even more convincing boat wake. And we can do the same again in 3D to get a really realistic looking boat wake. So in summary, boat wakes have the shape they do because water waves travel at different speeds. Slower water waves create narrow, closely spaced V-shaped wakes, and faster water waves create wider V-shaped wakes that are farther apart. When you add all these different V-shaped patterns together at the correct angles and spacings determined by water's dispersion relation, you end up with the unique shape of a water wake.
There you go.
Okay, there are some caveats to the science in this video, and you can find out about them in the extended version over on Nebula, the Streamy Award-nominated independent streaming service that's
Okay, that's a... And there is another one that I liked it. Shockwaves.
You're listening to my voice over time. Let's do an experiment and see what it sounds like if all the words I've spoken so far come to you all at once. Ready? Yeah, that's loud and also incomprehensible. But in editing this, I merely place the words on top of each other. The duration is still about a second. Let's squeeze the volume of all those words down to an instant. Ready? I don't want to hurt your ears nor kill the speakers you're listening to, but you get the idea.
That's the shockwave, right? The shockwave that you hear from an airplane under supersonic speed. That's the analogy that he's making here. How can we reproduce the shockwave of an airplane, right? Just put all the words that he spoke at the beginning in all together, spoken almost simultaneously, right? And you get that unpleasant sound.
Lots of sounds scrunched into a single moment provides a powerful punch. What you hear is a kaboom. A firecracker is giving you a bunch of sounds at once, which is why it goes kaboom. Remember how the water waves look?
See, this one is simplistic, right? It's far more simplistic than the previous video, right? In that previous video, he said that there are a bunch of wavelengths that are in the water that this bug excites. But here he's going to be, simpler. He's not going to elaborate on water waves like the other guy elaborated. Either way, he leaves this nice cone forming in the wake of the bug?
When the bug is traveling faster than the wave speed, you get trailing bow waves. And here we're talking about water waves, but sound too travels in waves. What happens when an object travels faster than the speed of those
Oh, here you go. All the wavelengths being compressed. See here?
sound waves, which is about 767 miles per hour? Answer?
Do you see the cone becoming sharper and sharper? Let's play a little bit more. There are so many nice videos here in the internet, right?
Was faster than the speed of those sound waves.
At this point is 90 degrees. The tangent is 90 degrees, right? You shouldn't measure this angle like that. You should measure this angle with respect to the tangent where all those circles are bunching up together.
Which is about 767.
And now the speed is increasing. The speed is increasing, the angle becoming sharper and sharper. The angle of the cone is becoming sharper and sharper.
Miles per hour. Answer? The same thing. Sound waves pile on top of each other along this trailing edge. Except the sound is three-dimensional. So rather than a V, what you get is a cone, as shown here. There are actually at least two cones, one of very high pressure.
Yeah, see, he's elaborating now. There's two cones, one cone of high pressure, the other cone of low pressure.
Where air molecules have been scrunched all together, and the other of very low pressure, where the air molecules are spaced apart. It's called a shock wave, and it trails behind the faster than sound object, such as a jet or a speeding bullet. In a shock wave, lots of sounds are hitting you all at once.
Boom, boom, boom.
And that's commonly called a sonic boom. Good energy.
Okay, that's I wish I had those things during my time. Okay, so now you should have a better idea how the Doppler effect works, right? And how shock waves are formed as well. What we have to do now, we have to do the relativistic Doppler effect. And I have a simulation for that as well. Let me add the links of those two videos, right, for you, so you know where to go. That's one. Shockwave videos. That's one. And that's the other. Yeah, what a lousy link. I don't like this link. Let's see if I can do better than that.
Para tratar os sintomas da gripe, conte com a gripe
Okay.
na gripe 7, o poder do gripe contra a gripe.
Okay, yeah, much better link, right? Why he gave me all that mess, I don't know. Here you go. You can look at the Wikipedia link as well that I showed to you. Shockwave. Wikipedia link or shock waves. Okay. Take a quick look. If you want to watch it, take a quick look at this video right now while I get something else for you. Okay, let's stop recording here. Now we're recording again. Let's not forget July 3rd, 2023, right? So what's happening here? Let's go back to our simulation, right? Here you go. At time t equal to 0, we have this referential B that's passing by a light source. Okay, and at the same time, the light source is emitting a wavefront. And because the wavefront travels faster than the referential, you're going to see that the wavefront is going to get ahead of the point that is also moving in the same direction, okay? Next, 6 seconds, right? Next, 8. Next, 10. Notice that the first wavefront is ahead of the ship. And now we have the second wavefront that's emitting. That's coming out from the source. It can be a star, okay? 16 seconds. Then sometime around here, let's see, 19. Let's try 19. Yeah, the second wavefront is going to catch up with the referential B. Make sense? That's what we have right in here. So what this guy is going to measure? This guy is going to measure that the period of this wave, is going to be that instant of time from 0 to instant of time 20. That's what this ship is going to measure. Okay, because that's what he's sensing right now. He's sensing the second wave front passing by him only now. Okay, whereas in a referential that is at rest, the period of the wave front is not 20, but it's going to be 10, because that's the exact moment that the wave front is being emitted, okay? So we use this point here in time to determine the wavelengths of our source. The actual wavelengths of the source, which is this distance right here, plus the speed of the moving referential, is going to be the speed of the light times instance of time t. We can go ahead and write down this equation. Okay, looking at, let's see, consider, right, a moving referential, considering a referential A, which is at rest with respect to u. In this referential, there is a light source of wavelengths lambda and frequency f, or period t, right? A moving referential B passes by the origin of referential A at time t equal to 0. Also, at t equal to 0, the light source emits its first wavefront. Okay? That travels at speed c. Okay? The wavefront moves ahead of referential B. Why is that? Because C is greater than V. I'm going to put B of A, okay? Velocity of B with respect to A. A moving referential B having a speed, right? Having a speed VBA passes by the origin of referential A at time t equal to 0. Also, at t equal to 0, the light source emits its first wavefront that travels at speed c. The wavefront moves ahead of referential B because C is greater than VB A. I'm just summarizing, right? What that illustration, that simulation told you, right? Then at time t equal to t with respect to referential A, a second wave front is emitted from the source. Okay. This is the period of your wave. This is the period of your wave with respect to A. Eventually, this second wave front catches up with referential B. Okay. At this point, the instant of time, this instant of time corresponds to the period of the wave. That catches up with B, right? Looking at the illustration, we have the following. Like that. Going back to our illustration again, here you go. The wavelengths of the wave plus the distance traveled by referential B must be equal to CT. Okay, so lambda plus VB of A times T must be equal to CT. Okay. But let's not forget that lambda is going to be what? It's going to be, let's not forget, right? I'm going to put it in a different way. That C must be equal to lambda times the frequency as measured by someone in referential A, which can be rewritten, right, as C divided by F. And then I will pass this term to the other side. And then, according to referential A, it takes this amount of time for the second wave front to catch up with referential B. Okay, and I'm gonna solve for that. This is the amount of time that someone in referential A measures. This amount of time that someone in referential A is measures that the second wave front, right, catches up with referential B. And it's also, it's also the instant. This is also the instant. This is also the instant that the referential B will measure the period of the wave. Okay. But recall from time dilation, right? That this period is also given by what? T, this gamma TB. Okay. Or we can here write that gamma is what? Gamma is greater than 1, right? So TB is going to be T over gamma. That's the relation between TB and T. Okay, and let's write it down, that this is the period that referential B measures for the wave. Okay. This is the period that someone in referential B, period of the wave, right? The period of the wave that someone in referential B measures. Now let's get that other relation, right? Let's put that in the proper format, right? TB, I'm gonna put here TB right in that. This gamma is going to be what? This T is gonna be what? No, first let's find out what T is, right? First, let's find out what T is. Well, what T is no. Well, first, let's use, right, that what we found for T before, right? Substitute what we have here, what we found before. That's the amount of time that takes according to someone in referential A. Here you go. This relation here goes right in here. I'm gonna put it here. No? Boldface. And then we're going to simplify that more. This guy goes downstairs. What stays upstairs is C. And then this gamma is going to be, oh, we can do something else. I'm going to factor the C that is here. So I can cancel out this other C. Right? When I factor the C that was here, we have to divide the VBA by that. I do that because I want to cancel the C with this other C. And there's one more reason. There is one more reason. Recall that this gamma is going to be what? The inverse of the square root of 1 minus BB of A square over C square. Like that. Now, do you understand why I factor my C? I factor my C because I will be able to cancel out something that's here inside my square root. Okay. In physics and math, what we're looking for simplifying equations, right? Mathematical equations. And that's what I'm trying to do right now. And this gamma is no longer, we don't need gamma anymore here. Because I already spelled out what gamma is, right? In the next step, we here write what is this factor inside the square root. It's going to be something like that. So 11:36, right? We should go for our break very soon. I'm going to put my T sub B here. Okay, that's the period that our observer from inside referential B is measuring for that light source. And I am going to cancel this one out. Use the other one downstairs. And when I do that, effectively, I end up dividing this term. Okay? Even better, I'm gonna do better than that. I'm gonna put it, this is square root right in here. Okay? let's not forget that this term here on the left side is going to be the frequency as measured by someone in referential B. 1 divided by F sub B. Like that. And then we have our relation. We are going to invert this equation that go F sub B. All I have to do is to invert the signs here, negative here, positive here, and then we have to invert this guy here as well. Okay? And now note C that the frequency measured by someone, the frequency of the star, right? Measured by someone. This term here is less than 1 because this term here is less than this term here, right? So consequently, F of B must be less than F. Like that. That's, what you see here is the frequency that someone in referential B measures for a source referential measures when it moves away from the source. So-called redshift. Redshift, right? If you repeat that for the case referential B is moving towards the source, you get the inverse, the blue shift. And the blue shift is going to look like just like the previous equations, but with the signs switched, the signs of the velocity switched. Okay? Moving towards the source is perceived to become bluer, right? Moving away from the source is perceived to become redder. And that really happens in real life, okay? Then the effect that we call red shift and blue shift. And that's what we have for relativistic, this is the relativistic Doppler effect. Okay, let's compare the equations that we had like before. Go. You go. That's this one is not for the relativistic Doppler effect, right? For the regular Doppler effect, we have what is seen below, right? The frequency change, right? But the frequency change because the relative velocity changes. See the difference? The frequency change because the relative velocity changes. The frequency change because the relative velocity upstairs and downstairs change. But in the case of the relativistic Doppler effect, the relative the relative velocity doesn't change. The relative velocity cannot change because the speed of the light must be the same in every referential. So something else has to change. And what changes, what actually changes is the period of the source. Consequently, the frequency of the source. Okay? Comparing the regular Doppler effect, with the relativistic Doppler effect, we have the important difference. In the regular RD, right? In the regular Doppler effect, the frequency changes because of the relative speed of the source the relative speed of the wave, right? And the relative speed of the source and the observer, okay? In the relativistic Doppler effect, the frequency changes. The frequency cannot change because of the relative speed of the source and the observer. Since the speed of the light must be the same in every referential. Instead, what changes is the period of the source due to time dilation. Okay? So it is the phenomenon of time dilation that affects the frequency of the light. Okay? The frequency of the light. The frequency of light. Yeah. That's the important difference between the relativistic effect, the relativistic Doppler effect, and the regular Doppler effect. Okay. Let's have our break now, or a half an hour break. Any questions about that? I'm gonna pause my Okay. What? 31, 46, 16. Até 12, 16, né? Tinha colocado 12, 1. Era até 12, 16. É. I said I put 12:01, right? But it was 12:16. Just note that. Our half-hour break. Can you hear me well there? Yeah, okay, thank you. So let's see. Some students are here. Let's make sure they get attendance. Kyriakos, are you there? Yeah, okay, good. And I saw, who else I saw here? Aimee, are you there? Aimee? Yes, okay. Anybody else? Okay, looks like someone left. Let's leave it this way for now. Okay, good. So let's summarize what we did for the Doppler effect. Summary of the relativistic Doppler effect. Okay. Things that we do with relativity, is very simple from the mathematical point of view. It's very simple. Most of the things that we do in relativity doesn't require calculus. So far, we have been dealing only with algebra, right? But the ideas, how you use all those concepts, they are very difficult can be very challenging to apply, okay? And I'm going to repeat what happened here to the relativistic Doppler effect. Hopefully you're gonna have a better idea, right? So I'm gonna copy what we have here. Let's see here. $12.20. Hey, wait a minute. We have a lab now, right? Yeah, we have a lab now. Let's do it. Instead of continuing with the lecture, let's continue. Let's start with the lab, and I'm going to walk you through how to find out your grade. That's going to be lab number 4. Yeah, so let's do let's do the lab, right, instead of relativity. Next time I talk about the relativistic Doppler effect, okay? Summary of the relativistic Doppler effect, and I'm going to put it right in here. Tomorrow is going to be, tomorrow's going to be the 4th of July, right? It has to be the 5th of July. I keep that here so we can all be reminded that I'm going to summarize what we did for the relativistic Doppler effect. And before we start the lab, I want you to do the following. Go to, let's see, how to read your grade from the file I uploaded to your group folder. Okay. Insert page break. 1. Go to your group folder and download the following. Download to your hard drive the following. A. An HTML file, HTML format file, and this file is P39 lab01 group, right? xx.html. HTML. Let's go there. Let's make sure everything is in exactly what I wrote down here, right? Here you go, P39, L01, GX, right? Let's put that GX 18. So there is this file, and then there is this folder. You have that download both of them. And download and underscore files and download the following and to the folder okay, so that's what you have there. You're going to need both of them. If you're group 5, you're going to download this one, right? If you're group 4, you're going to download those two. HTML here. Let's do that. I'm going to do that for group 4 for now. Okay, download it. Look for the file and the folder. Download it. This, when you do that, he's going to zip those two documents. And most likely he's going to download it to your download folder, most likely. Okay. Two. After download, during downloading, this document, right, will be zipped / compressed, and most likely will be saved in your download folder. Depends, sometimes depending on the setting of the computer, right? You may download it somewhere else. In the past, my computer used to save those things in the latest place that I worked on. Everybody did that? Let's do that. And in the meantime, I'm going to take this chance and take attendance. First step. No, not this one here. Roster. And that's going to be attendance lab now. Today is the 3rd of July. Amy, are you there? That's attendance for, okay, good. Alisa, are you there?
Here.
Okay. And I have a question, right? Did you download the file in the folder? Alisa?
Yeah.
Yes. What about you, Amy? Did you download the file in the folder? Let's see. Did you say yes, Amy? Okay, yeah, she said yes. Okay, next. And Sartak? Yeah, yes, download the file. Okay, good. Oh, I meant Ashley. Okay, Ashley, are you there?
Yeah.
Okay, did you manage to download it?
Yep.
Okay, so the next step, right, before I continue with the attendance here, go to what I want to know from you, everybody, right? where your file is downloaded to, right? In my case, it's downloaded to my download folder. So if you might want, just type there in the chat box, I would appreciate. Okay, where it ends up. Mary, are you there? Doesn't look like Mary is here, right? A download folder. Okay, Ashley, thank you. Mary is not here. Raymond.
I'm here.
Yeah, did you manage to download the folder and the file?
Yes.
Where did it end up?
It's in my downloads.
Folder. Okay, that's good. Okay, in the next step, I'm gonna go back here to the. Here's my download folder. Where is that? Yeah, here you go. Here's my download folder, right? The downloaded file is this one. And remember, I was downloading group 4, right? What you have to do, you have to highlight the file and the folder and copy them. Okay, so next step. Locate your downloaded folder and your zipped folder, right? Your zipped folder. And go inside it. And go inside it. Locate your zip folder. Double click it. And copy the contents. Okay? Just like I did, I copied the contents. After copying the contents, get out from the zipped folder and paste the contents you copied. Okay, that's how you do it. And I'm gonna show that to you. I'm here inside. I'm gonna copy the contents, go outside. You can go anywhere, provided it's outside the zipped folder. Paste it here. Okay, and now I have the file and the folder of group 4. And I'm going to work, see HTML file here and the folder here. This file and the folder must be in the same folder. Otherwise, the program is not going to work well. Okay, so going next here. Basilio know how to do that, right, Basilio?
Correct.
Okay, so next is Jeshuan. Are you there, Jeshuan?
Yes, I downloaded and did all that.
Okay, did you copy and paste the contents outside?
Yes.
Okay, good. Now the next step is straightforward. All you have to do is to double click on the HTML file. Can I do that, group 4? If I double click here, I'm going to have to expose your grades to everybody else here in the course. Group 4, are you there? Is that okay? Are you sure? Oh. Okay, so if you double click, you're going to see something like that, okay? With blue colors. These blue colors that you see here, and the red colors. The red colors are the units that are not correct, okay? The blue colors is the significant figures that are missing. Blue colors is missing significant figures. Anything that's colored here is a mistake, right? And then here, incorrect units, right? If you miss loss of units, I subtract 3 points from each unit that you missed. 0.8 units that you missed from the significant figures that are missing. 0.4 units that you add of the significant figures that you added incorrectly, and so on, right? And then there are other things too. I look at the graph that if it is optimized or not, okay? I look at the graph labels of your graphs, the graph of the units in your graph labels. That should be, -1 point. Make sure you have the proper title to your files. R-square, values of the graph, and the regression equation, okay? That's how I do that. And basically, that's what you need to know. The grade is at the top of the document. Okay, and that's what you need to know to find out your grade. Is that clear? Let's see. Let's continue. Zaid, are you there? Not open in Google. Yeah, actually, you have to download your HTML file. Okay, you cannot open inside Google. You have to download your HTML file in that folder to your hard drive. It will not open in Google. Okay? That's why we went through those steps, right? Don't forget, the steps are here. And paste the contents you copied. 5, double click in your HTML file. Oh, you downloaded and tried to open the file. Okay, which group are you, Ashley? Group 1. Okay, remember, make sure you don't, you wrote that down here. My HTML file won't open in Google. That's right. It will not open in Google. You're right. That's why you have to download your hard drive, right? So I'm going to download make sure that you download your hard drive. Once you downloaded your hard drive, you'll be able to open the file. Let's see here. Let me download your file. Take that. Yeah. Okay, good. Group 1. Okay, here you go. HTML file. And then, okay, Ashley, go step by step with me, right? And then you gotta click on this one too. Did you click on this other one? On the folder? Gotta click on the HTML file, and then you click in the folder. That goes for everybody in group 1. And I'm gonna right click, download, right? Must be this one. No, yeah, no, this one here. Showing folder. Let's make sure your files are here inside. Highlight both the folder and the file. Copy. But I don't see if can open it. Okay, let's see. Let's see if I can open. Maybe you gotta paste it here outside this zipped file. Okay, here you go. File and folder. Can I open your HTML file, Ashley? Yeah, let's see. Let's see. Yeah, I can see it. See that? I can open it nicely. Hey, wait a minute. Something wrong here. Uh-oh. It looks like Why is it here? Oh no. Let me see. Actually, looks like I pasted the wrong one. Yeah. Okay. Makes sense now. Okay. You were not able to open it, you said? Let's see here what's going on. Looks like I got some other students file there for you. Let me stop sharing momentarily, and let's figure out what's going on.